And welcome to the third part of our 25th lecture for Math 23. So I lied a bit at the end of the second part. I thought that I could find some examples where rearranging the order of integration would be of benefit for triple integrals in Cartesian coordinates over rectangular boxes. But I'm not able to come up with some examples that work the way that I want them to do. This is a topic that's better suited had we not cut these type 1, type 2, and type 3 regions in Cartesian coordinates. So just forget that. What I claimed was going to happen in part 3 today is not going to happen. Instead, we're going to think about one general theorem here quickly that tells us how to find volume as a triple integral. This is analogous to the theorem that we considered in part 1 of today's lecture, where we found area as a double integral. And then we're going to begin thinking about cylindrical coordinates, our first non-Cartesian coordinate system for 3 space. So just as the double integral of integrand 1 over some region with respect to area gives you the area of that region, so also the triple integral of integrand 1 over a region with respect to volume will give you the volume of that region, a subset of R3. And that's stated here in this theorem. Volume is a triple integral. If R is a region in R3, the volume of R, given as V of R for volume of R, is just the triple integral of integrand 1 over the region. So this is not going to be of as much use to us yet, but will be of greater use to us once we have considered cylindrical and then spherical coordinate systems. Right now, the only kind of region that we know how to integrate across in R3 are rectangular boxes. And for those, volume is actually not that interesting. It's just the length times the width times the height. So we already know how volume works for boxes. But ultimately, this theorem will allow us to compute the volume of more interesting regions once we are able to deal with the different types of regions as we start to think about cylindrical and spherical coordinates. So, one more time, you can find the length of an interval by taking the integral of 1 across that interval as a single integral. You can find the area of a region of the plane by integrating constant integrand 1 as a double integral over that region of the plane, and you can find the volume of a region in 3 space as the integral of constant integrand 1 over that region in 3 space. And we will return to this theorem as we gain the ability to take triple integrals over regions that are more interesting than a rectangular box. And to that end, we will begin to consider the cylindrical coordinate system. So this is chapter 15.7 in Stewart, if you would like further reference. Cylindrical coordinates can be characterized as polar plus z is the big idea, but we can also formulate them as polar plus y or polar plus x. So the idea is that you take one of your coordinate planes, traditionally the xy plane, and you represent that plane in polar, and you leave the z-axis as it is in rectangular. You can also represent either the xz or the yz planes in polar and leave the remaining rectangular variable as itself. So if we represented the xz plane in polar, the y variable would remain as the y-axis, and we would have polar plus y for sort of a sideways representation of polar coordinates. We'll focus first on polar plus z, that's the traditional setup, but we will also consider how it can be adapted to deal with some situations that are more naturally represented if cylindrical is given as polar plus y or polar plus x. So what's meant to be represented here is I've got the xy plane flat, but it's represented as the r theta plane. So this is the origin here. We've got theta lines, lines of constant theta, theta equal to 0, theta equal to pi over 4, pi over 2, 3 pi over 4, and so forth. We've got radial lines, which are our circles centered at the origin. And we have our z-axis sticking up out of the plane in polar. So take the xy axis, represented as polar, but then from the origin, extend the z-axis in the positive and negative directions, and you will have a representation of cylindrical coordinates as polar plus z. So in rectangular, excuse me, we have our x, y, and z variables, and our dv expression in our integrals looks like dx, dy, dz. In cylindrical, we're dealing with our r, theta, z variables, and our dv expression is going to look like r, dr, d theta. That's what dA looked like in polar, and then dz, the term from rectangular still. So our dv expression looks like this in cylindrical. There are pictures you can draw to think about what a unit volume element looks like in cylindrical, and those are given in Stewart chapter 15.7. I won't re-represent them here, just in the interest of time. But this is sort of what does a little rectangular box look like in rectangular? Well, it looks just like a box. Delta V would be delta X, delta Y, delta Z. In cylindrical, you would have the same kind of dA term that we've seen before. So this was a little quote-unquote rectangle in polar, where the area actually depended on how far away from the origin you were. We discussed this when we talked about polar, but now it's going to be extended through the z direction just by a delta z term. So we've got our delta A from polar here, and a delta z expression analogous to what happens in rectangular to get our dv. Or we could do cylindrical as polar plus y or polar plus x. We would have r theta y and a r dr d theta dy dv term. Or we could have r theta and x as our variables, and our dv expression would look like r dr d theta dx. Again, this is polar plus y or polar plus x. Generally, we'll work in polar plus z, but I do want to highlight now and later as well when we do some problems how that can be adapted to these two other formulations of cylindrical coordinates. So just as before, when we're dealing with a new coordinate system, one of the first things we want to know is how to translate from one coordinate system to another. And actually, we don't get a lot of new information here, as cylindrical is polar plus z. And we've already thought about translating from the xy plane to the r theta plane, and z remains z. So x is our cosine theta and y is our sine theta, just as we saw when we were dealing with polar in 2 dimensions, and z remains z from rectangular to cylindrical. It plays the same role in the two contexts. And likewise, if we want to go the other way, r squared can be given as x squared plus y squared, or you could write it as r being the root of this sum of squares. Tangent of theta is y over x. There's also an expression for sine of theta and cosine of theta. You could write any of these in terms of the inverse trig function, so theta is tan inverse of y over x, and so forth. And z is just z. The expressions for theta don't actually get used as much. The most important of these to remember is equal to z is relatively easy to remember. The most important that might take a bit of thought is that r squared is x squared plus y squared, and again, that's just Pythagoras' theorem. So the next thing that we're going to do at the beginning of next lecture is, again, the purpose, the utility in having multiple coordinate systems is that some integrals will be easier in one coordinate system than they were in another. So we had the rectangular coordinate system. There will be certain types of regions that will be difficult to represent in rectangular coordinates. These types of regions might be particularly easy to represent in cylindrical coordinates. And so if we're working in a coordinate system which is more naturally adapted to the problem at hand, that's going to make the problem easier. You're sort of coming to the problem on its own terms. You're not trying to fit a round peg into a square hole, for instance. So cylindrical coordinate systems, the purpose of them is to make hard problems into easy problems by giving us a method to compute integrals that will be simpler for certain types of regions. So the next question to arise naturally is, well, what types of regions are best represented in cylindrical? We need some kind of intuitive understanding of what types of regions are well represented or are naturally represented in cylindrical, because those will be the types of regions which, if we want to integrate over those regions, we will want to do so in cylindrical coordinates. So next time we are going to think about what rectangular boxes look like and what grid surfaces look like in cylindrical coordinates. When we first discussed polar, we thought about polar rectangles and we thought about grid lines. Here in 3 dimensions, we're going to think about cylindrical boxes, quote unquote, or cylindrical rectangular boxes and grid surfaces. And we'll begin that next time.